Welcome back, everybody. In my previous video, I went through every single equation in a classical mechanics final exam, just some random equation sheet that I found. Today, I have a practice final that I found online. We're going to go through it. I'm not going to go through this as if I'm in the final because I don't have time right now. I'm sorry, guys, but I'm going to run through it very quickly. Maybe I'll skim through some stuff. I'll just give you guys my idea of what I'm thinking, and I think you guys can piece the rest of the stuff together. Obviously, practice a lot. You know, you want to have experience doing some of these problems, so practice as much as you can. But in this video, my goal is to just show you how I'm thinking about this. You can kind of test yourself if you've done an example like this, or you read the problem with me and you can kind of predict what I'm about to say, or you can catch my mistakes and you can see kind of like what the correct answer is. Then you are ready to go for the final exam. So hopefully this video is helpful. And maybe we can learn some new stuff together. Again, let me know if you have any questions or you have specific problems that we can try out together, and we'll take a look at it. So first thing I do when I go into a final exam, you need a watch, right? Bring a watch so you can time yourself and you know how much time is left, because you don't want to be left with like 6 big questions to do with like 20 minutes in the exam. You want to have some time. So normally final exams like this are 3 hours long, but base yourself based on how much time you have. So I'm going to like open up the exam, and here I'm going to take a look. These are multiple choice. We have 1, 2, 3, 4, 5 on this page. We go until number 15, and then over here is the long answer ones along. It looks like we have 1, 2, 3, 4, 5, 6, and this is my little equation sheet with my drawings from the other day. So I'm gonna quickly go through this. Normally what I do is I just scan and read every problem before doing anything, and then if I find something interesting, I would just write it down. I'm not going to start doing any work until I've scanned every problem, but we'll see how everything goes. And I like doing this because if you just read a problem, your brain will kind of remember it and it's going to work in the background. And also, sometimes there's hints in other questions that may help you with a question in the future. So you want to read everything so you get kind of a big picture overview of the exam, and then you can kind of prepare and do everything and allocate time to whatever is most important. Also, if you're running out of time, look at what question is worth more and focus on that so you get more points, or look at what question is easier and do the easy ones first so that you get those easy points out of the way. Anyway, we're going to read this. Read it along with me. Try to solve the problems in your head. And again, let me know if I make any mistakes. I'm a human being, you know, I'm not a machine, I'm not an AI, and I have not seen this exam before. I haven't read a single thing, so this is me just blank looking at this. I'm going to use my mind, my memories, my experience of doing these problems, and also the equation sheet. Question number 1, multiple choice. Alice and Bob are standing on a rooftop of a 5-meter tall building performing the following experiment. Alice drops a ball of mass 1 kilogram, and at the same time, and from the same height, Bob shoots a 0.1 kilogram bullet horizontally with a speed of 500 meters. Which one hits the ground first? Ignore resistive forces. I feel like answering this. I'm going to speak, and we're going to look at the other problems later. But normally, if I'm in an exam, I'll just very quickly read this and be like, do I know how to do it? Move to the next problem. First thing that comes to mind is the Mythbusters did this experiment where they drop a bullet and they shoot a bullet, and the bullets fall at the same time and hit the ground at the same time. But in this case, the bullets were the same mass. There's another experiment I can think about, which is a flat piece of paper and a crumpled piece of paper, the same piece of paper, so the same mass. The crumpled piece of paper falls faster because the flat piece of paper is like affected by wind resistance. There's another experiment where they dropped a hammer and a feather in a room with no air, and they also did this experiment on the moon when they visited the moon. The feather and hammer drop at the same rate. So regardless of mass, things accelerate to the ground at the same rate, which is the rate of Earth's gravitational acceleration, 9.8 meters per second squared. I can also remember this one scene in Tom Holland's Spider-Man 1 where he's kind of distracted in class and the teacher's talking about classical mechanics in the background, and then Flash is like making fun of him because he's distracted, and the teacher's like, Peter, what do you think the answer is? And then he goes like, mass cancels out, so acceleration is g. So from that, I can remember like, the mass in the equation for this cancels out. So irregardless of the mass of the object, they all accelerate and drop at the same time. I don't know if that was too much information. I don't know if you guys have the same memories as I do. Obviously not. But for just that, I'm going to say they hit the ground at the same time. But maybe I'm going to be like, the ball is heavier, so maybe it drops on the ground first. Put a little question mark, but I think they hit the ground at the same time is good. I'm going to keep going because I don't want to waste too much time on the multiple choice. Number 2, a projectile that is launched horizontally goes down 1 meter in the y direction after going forward 50 meters in the x direction. What is the initial velocity? Take g to be 9.8 meters per second squared. Round your answer to the nearest integer. A projectile is launched horizontally, goes down 1 meter in the y direction, y, after going 50 meters, 50 meters in the x direction. What is its initial velocity? Round your answer. So I'm thinking velocity goes like this direction, right? And it falls down one. Oh, this is a tough one. I'm gonna skip it. 1,000 kilogram car drives up a semicircular hill with radius 10 meters. With what maximum speed can the car go over the hill without leaving the surface jumping? Take g to be 9.8 meters per second squared. Round your answer to the nearest integer. Damn, this one's hard too. You know what? I'm gonna skip this one too, because I'm not too sure. Like, oh, maximum speed. I have a feeling it's 10, just because it's like the number that's closest to 9.8. And I'm thinking if you go faster than g, you like start flying, but this is in meters per second, the speed, and g is acceleration, meters per second squared. So, and hill with radius 10 centimeters, so it is a hill like this, and the radius is 10 meters. So, oh, I'm thinking something like this. Centripetal acceleration is v squared over r, right? And if the centripetal acceleration is greater than 9, so we put 9.8 meters per second squared in the acceleration thing, and then we put 10 meters here, then we can solve for this v. Does that work? Does that work? But that doesn't make sense because 9.8 times 10 is 98 meters squared per second squared, and then you square root this, and 98 square rooted is around 10. So maybe that makes sense. You know, I'm gonna put my answer as maybe 10, but I'm not gonna circle it just because I'm a bit confused. So I'm gonna keep going. So far we are 7 minutes in. A block A with mass m slides on a frictionless floor with constant speed v. Okay? It then collides with block B with mass m, which is at rest, and it completely sticks to it. What percentage of the kinetic energy of block A converts to kinetic energy of the two blocks after the collision? So this block is moving, and this is block A, and it has mass m, and it has speed v. By the way, you don't have to show any math for this multiple choice. You just have to circle an answer. So any of the calculations here that I do are useless, but for me, drawing a picture is kind of nice, like it helps me a bit. Then it hits block B with mass m, which is at rest. So this is block B. It's mass m and it's at rest. And then after the collision, these blocks are now glued together. And I'm assuming they're still sliding because of conservation of momentum and energy and shit like this. So what percent of the kinetic energy of the block A converts to the kinetic energy of the two blocks after the collision? I'm tempted to say 100% because of conservation of energy. So, but maybe we can find kinetic energy of block A, kinetic energy of block B, and then kinetic energy of block A plus B. And maybe there's going to be some kind of thing that we can do here. So let's do it real quick. So we have 1/2 m v squared, and then the kinetic energy of this is 0. And then this one is 1/2 2m because it's m plus m. And then what is the v here? It then collides. Yeah, they don't tell us the final V. I'm not sure, but I'm thinking that it is 100%. Yeah, because they don't say kinetic energy goes anywhere. So it hits the block, they keep sliding. If everything is like perfect, I don't know. We're gonna go with A, but I'm gonna leave it as is for now. In car accidents, how do airbags save passengers' lives? They decrease the change in momentum of the passenger compared to a car with no airbags. They increase the interaction time during which the passenger is brought to rest and hence decrease the force applied to the passenger. Automatically, I know this one because I remember impulse is force times delta t from the equation sheet. And I remember the only example I remember from impulse is something to do with airbags. Like, if there's no airbag, all the force that you feel from the crash is just going to slam your body into the like steering wheel. But the airbag is your force is not changing. You're still hitting like if you have two example crashes at the same force, but there's one with an airbag that's kind of like dissipating the force over an amount of time, and another one without an airbag where all the force is just boom, like instantly hit. The impulse is higher or lower. I don't know, but let's read C. Airbags do not affect, this one is automatically whack, because why would we have airbags if they do not affect the force applied? They only allow for more time for the body to adapt to this force. Ooh, actually, I don't know. This one's interesting. They decrease the change in momentum of the passenger compared to the car with no airbag. They increase the interaction time during which the passenger is brought to rest and hence decrease the force applied to the passenger. Maybe this one. Airbags do not affect the force applied to the passenger. They only allow for more time for the body. You know what? Now that I'm reading it, these two seem the same. Decrease the force applied to the passenger. Airbags do not affect the force applied to the passenger. They only allow more time for the body to adapt to this force. Oh man, maybe C. So I don't know, maybe C, but maybe B. I'm gonna circle B and then go back and think about C. In a figure, what time do we have? 12 minutes. Not bad. In a figure skating tournament, Alice is spinning with her arms fully stretched. Suddenly a bird sits very slowly on her hand. What happens to her angular speed? So if I'm imagining a figure skater, if the figure skater is spinning with their arms out like this and then they pull their arms in, they spin faster, right? Because like moment of inertia decreases or something like this. I'm not sure. But if a bird lands, like imagine it's not a bird, but imagine you're spinning and then I give you like a 45-pound like weight to hold. You're gonna kind of spin slowly because there's more mass there. So I think what happens to our angular speed, it decreases. Yeah, I think that's good. A ball and a box are placed next to each other on a frictionless inclined surface. If we let them go at the same time, the ball rolls without slipping and the box slides down the inclined surface. Which one will have a larger velocity of center of mass at the bottom of the incline? Although the surface is frictionless, assume the ball rolls without slipping. The ball, the box, they will have the same velocity of the center of mass since they were released from the same height, cannot be determined. This one is tricky because it's something to do with kinetic energy. So the ball, I think, has moving kinetic energy and also rotational kinetic energy. So I think the ball moves faster. I'm just going to say the ball because I don't want to waste time, but I will think about this. Something related to kinetic energy. I remember seeing a problem related to this. Two bullets with the same mass and velocity are shot through two boxes that have the same mass. In A, the bullet enters the box along the line passing through its center of mass, while in B it does not. As shown in the figure. If the bullets come to rest inside the boxes, which box will reach a higher height? They will reach the same height. I know this for a fact, bro, because I remember doing this problem previously. I remember watching a Veritasium video where they did this experiment. It's bamboozling. I still don't understand it, but I know they reach the same height, so I'm just going to write this down and keep moving. I know this is like a correct thing, so I feel good about this one. Unless like the grader changed the answer or something like this. A bar magnet of length L and mass m is spinning about its center of mass with constant angular speed omega on a frictionless surface. We slowly push an identical bar magnet on the surface close to it until it sticks to the spinning magnet. Ignore the effect of the magnetic force and assume it is only responsible to stick the two magnets together. The two magnets with length 2L then spin with an angular speed omega prime about their center of mass. What is omega prime? The moment of inertia of the bar magnet is... Okay, so we have one bar magnet, length L, mass m. Length L, mass m, spinning about its center. And it has an I moment of inertia of this. And angular speed of this. We are asked to find angular speed omega prime, which is one of these guys, right? until it sticks to the spinning magnet. The two magnets with length 2L then spin with an angular speed about their center of mass. So now we have one magnet like this. Maybe it's a bit longer. Let me erase this. One magnet like this, and then another magnet like this, and I put a dot at the center of mass. But now they're spinning about their center of mass here, and this now here has length 2L because it's the length of two of these guys. And since the things are combined, it also has mass 2m. So what is omega? Oh man, I'm not sure about this one. I think I'm going to skip this one too. A mass spring system is in simple harmonic motion described by x as a function of t is equal to 3 cosine 2 pi t. What is the velocity at t equals t over 4 in meters per second? So what is the velocity? Man, you have to take a derivative here. So I know that x of t is equal to 3 cosine 2 pi t, right? What is the velocity at t is equal to this? So at x at t is equal to this period t over 4. And I remember an equation related to t over 4 in the equation sheet, so we might peep this. 3 cosine and then 2 pi, and then I'm going to put t over 4 over here. And let me just very quickly peep what is in my equation. T is equal to 2 pi m over k, and that gives us more symbols, so that spooks me a little bit. Let's go back. Oh man, and all the numbers are 0, like all this stuff here. But they're also asking us for the velocity, and I know v of t is equal to the derivative of x of t as a function of time. But I don't know if we have to use that because I feel like derivatives are not needed in this class. But what I'm trying to do here is solve for this, and then maybe that's going to give us some information. But how do we solve for this? When t is something unknown. I'm going to skip this one too, guys. Damn, I feel uncomfortable right now because I skipped so many. 11. A 12 kilogram block on a horizontal frictionless surface is attached to a light spring, force constant 800 newtons per meter. The block is initially at rest at its equilibrium position when a force magnitude P is equal to 80 newtons, acting parallel to the surface is applied to the block as shown. So you pull this block. What is the speed of the block when it is 13 centimeters from its equilibrium position? Oh my goodness. What is the speed of the block? So we are given a force constant, which is this spring constant. K is equal to 800 newtons per meter. And we pull it. The block is initially at rest at its equilibrium position when a force 80 newtons acting parallel to the surface is applied to the block as shown. What is the speed of the block when it's 13 centimeters from its equilibrium position? So this delta x, how much you displace it, is 13 centimeters, which I'm going to convert to meters, 0.13 meters. And then F is equal to, but this feels weird. Why are they giving us a force? And how do we get speed out of this? I'm going to go back to the equation sheet real quick. And I remember, sorry it's so messy here. I don't really want to delete any of these writings. I know that there is a spring constant thing over here. So this is the equation I'm trying to draw out. Here's the spring constant, here's the force that the spring provides, and here's the extension. So we're given an extension and we're given the spring constant. From this, we can figure out how much what is the force that the spring is pulling the thing with. But we also have a force applied to this block that is on the spring. So we have a force applied, and then when we extend the spring a specific amount, like let's say we stretch it this delta x, then there is also this force of the spring pulling us back. And then this thing will have a speed, but how do we get the speed, man? Maybe we combine F here with this F equals ma, but a gives us acceleration. Do we use one of these guys? Maybe this. No, I'm not sure. Actually, take a look at this. We have here acceleration we can pull out from this maybe. And then here we have the extension, and if we say this is 0, then this one maybe could give us an answer. This is how are they going to give this on a multiple choice, man? This is crazy. There's so many different little numbers that you can play with. 12 kilogram block. Okay, so let me think here. Nah, I must give this one too. Oof. 12. A disk, radius 8 centimeters, that rotates about a fixed axis, starts from rest and accelerates at a constant rate to an angular velocity of 4 radians per second in 2 seconds. What is the magnitude of the total linear acceleration at a point on the rim of the disk? Linear acceleration. So linear acceleration, automatically I'm thinking of A is equal to R alpha. At a point on the rim of the disk at an instant when the angular velocity of the disk is equal to 1.5 rads per second. I feel kind of good about this one. And the disk radius R is 8 centimeters, which I'm going to convert to meters. So this is in meters. It starts from rest. So this is omega final. Omega initial is at rest, so it starts at 0. And it accelerates at a constant rate to an angular velocity of 4. Oh man, so hold up. This is not the final one here. Cross that out for a second. Omega final is equal to 4 rad per sec, and time is equal to 2 seconds. 2 seconds. So what we have is omega initial, omega final, time, and then we can find acceleration. So if we find acceleration, what is the magnitude of the total linear acceleration on the rim of the disk at the instant when the angular velocity of the disk is 0.15? Okay, so this one I think I got. I'm gonna just write some extra work here. So I remember omega final is equal to omega initial plus alpha t, and what we're looking for is alpha. So omega final is 4 rad per second minus omega initial, which is 0 rad per second, and then on the other side we have alpha t, and then I'm going to divide by t, which is 2 seconds. So these numbers combine, and this seconds I think cancels with this seconds, and then we're left with rads. Or no, it combines with this one, so we're left with rads per second squared. Okay, so alpha is equal to 2 divided by 4, or sorry, 4 divided by 2 is 2 rad per second squared. So that's the acceleration, and we're looking for the total linear angular acceleration, which from this equation, from the equation sheet, you can plug this alpha in, and we can use this to find this. But we're not looking at it at this time. We're looking at it at over here. Oh, man. So now we have a new angular velocity. So this angular velocity is the new angular velocity 1.5 rad per second. We need to find the acceleration at this time. Wait a second. But it's constant acceleration. Accelerates at a constant rate. So I think this number here is put to trip you up. So I think we can just multiply 2 by this 0. Let me pull out a calculator. We can just multiply this, because this is constant acceleration. This acceleration is happening at this, and at this angular velocity. So if we just multiply this alpha over here by this, I think we should be chilling. Let me pull out a calculator real quick. 0.08 times 2, 0.16. And that's meters, so I think this is the answer. I think this is the answer, but not sure. All right, we're gonna leave it at that. Two melons are dropped from a second floor physics lab at height h above the ground. Watermelon B has 4 times the mass of watermelon A. When the watermelons pass the bottom of the first floor window at height h over 4 above the ground, the relation between their kinetic energies K and KB is equal to... okay, so they're dropped from the same height. When the watermelons pass the bottom of the first floor window at height h above the ground, the relation between their kinetic energies is... So will they have the same velocity? They have the same acceleration. And I think only their masses change. So since I'm gonna just do a quick answer here. Since kinetic energy is 1/2 mv squared, kinetic energy only depends on the mass and the velocity. I'm gonna assume their velocity is the same when they hit this place, but the mass of A is 4 times bigger than the mass of B. So the kinetic energy of A is gonna be 4 times bigger. So I think it's this one. Right? Because Ka is 4 times this. So this is smaller than Ka. You have to multiply this Kb by 4 just to get the value of Ka. All right, I think that's good. At this stage, I'm kind of freaking out because we've been through half an hour of the exam and I've solved probably like 4 questions. But that's okay, no stress. We're almost done. We got 2 more, and then I'm going to sweep through and see what we left at. 300-gram bird flying along 8 meters per second sees 10-gram insect heading straight toward it at a speed of 30 meters per second. The bird opens his mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing when the insect comes to rest inside the bird's body? What is this kind of... Okay, I'm going to model the bird as a block. 300 grams, 8 meters per second. This looks like a conservation of linear momentum. And then we have a little bug, which is over here. This is 10 grams, and it is, so the bird is going this way, and the bug is going 30 meters per second. What is the bird's speed immediately after swallowing? So I doubt the bird's speed is going to change much, but I doubt the bird's speed is going to increase because the bug is going the opposite direction, right? So it's not going to be 38. It's not going to be 6.8 either. It's not going to be 8. Maybe it'll be 19. Oof. 10 gram, 30. Okay, let's test it out. So momentum is mass times velocity. I'm going to just keep the units as grams here, which is a bit weird, but I don't want to convert grams to kilograms right now. If you want to, you can do this to keep everything in SI units, but it doesn't matter for me right now. So 300 grams times 8 meters per second is the momentum of the bird before the collision. And then the momentum of the bug is 10 grams times 30 meters per second in the negative direction. So I think after that you combine these. Can you just combine these? Yeah, I guess you add the momentums and you get the final momentum, which is 310 grams, and then velocity final. Like, what is the velocity final? So now we have this top equation, right? The momentum before and then the momentum after has to be conserved, I guess. So let's check out what we get here. And since I'm keeping all the units the same, it should work out to be good. So 300 times 8 is 2,400. Just write this 2,400 over here. And then we got minus 300. So 2,100 divided by 310. Ooh, interesting. It's going to be 6.8. Very interesting. Wait a second. This is the new velocity? Okay. This one. This is how I got it. I just did conservation of momentum. I don't know if this is right, but this is my first thought, and we're on the last multiple choice. me take a sip of tea real quick. A 5 kilogram mass is suspended by a spring from the ceiling of an elevator that is moving upward with a speed which is decreasing at a constant rate of 2 meters per second in each second. That's weird. What is the tension in the string supporting the mass? Ah, man, okay. Here's this. There's mg over here, and there's the spring, which normally the tension should equal mg. But now the whole elevator is accelerating upward. So this whole thing, this whole box is accelerating, moving upward with a speed which is decreasing. So the acceleration is slowing down. So does that mean... And then what is constant rates? 2 meters. 2 meters per second in each second per second. So is it just 2 meters per second squared? But it's decreasing, so it's negative? What is the tension in the spring? And then we have 5 kg times 9.8. What is this? So this is going to give us what the tension is without the elevator. 5 kilograms times 9.8 meters. This is 49. And I don't think that's going to be the answer because we have some kind of stuff going on. It's not going to be 9.8 because that's goofy. 45, 39, 59, all these feel good. So imagine you're in an elevator and you're moving up, but you're slowing down. So when you're moving up with a constant velocity, so no acceleration, then you don't feel anything because you're at a constant velocity. It's like if you're in the car on the highway, you feel nothing. But once you start slowing down, you feel like rah, like you're being sent forward, or if you're speeding up, you feel yeet, and you're being pushed backward in your seat. Let me think a little bit here because I want to get this final thing right. We got 33 minutes. Honestly, not bad for all the multiple choice. I mean, we didn't do all the multiple choice, but... So you're moving up, but you're slowing down. Okay, so if you're moving down in the elevator, then you feel like you're being pushed down a little bit. So the tension on the spring would increase. So I don't think it would be this 59 because that 59 is greater than 39 or 49. And if you're moving up, then you feel a little bit like weightless, like the elevator is kind of like throwing you up, kind of imagining like you're in a roller coaster. But is it enough to lower it all the way to 39, or is it just going to lower it a little bit to 45? And how is this 2 meters per second useful? If we do F equals M, which is 5 kg times 2 meters per second squared, this is 10. And then this 10 minus 49 is going to be exactly 39. You know what? I'm going to put this one. Hopefully that made sense with you guys. Let's take a big gander. We have 1, 2, 3, 4, 5, 6 long questions, and we have around 2 hours. Let's say exactly 2 hours. Give 30 minutes for buffer room, 30 minutes to do the rest of these. So I went through all the multiple choice. We did one. We have one question left. 2, 3, 4, 5, 6, 7. 7 questions left. Should we go through these? I'm going to skip them and just read the long answers. We're going to go back to the multiple choice later. Don't stress if you're in this situation. You know, I'm in this situation and I've studied this course many times, so we should all be good. Let's read these questions. A block of mass M is connected to a hanging mass M with a massless string through a pulley, as shown in the figure. The blocks are initially at rest. Draw the free body diagram of each block. Beautiful. That's easy. Okay, so I'm just going to draw this really quickly here. I'm not going to go through all of these problems in depth. I just want to show you guys how I'm thinking. Maybe I'm going to just speak and then write a few small equations to get the ball rolling, but I'm not going to write a full answer. So all of the forces, this guy feels an mg down here. It also feels a normal force up here. And did it say frictionless? Connected massless spring shown in the box initially rest. So there's no friction that they're talking about. And then there's a little tension over here. I think that's everything. This guy is being pulled down by mg. and it's being pulled up by tension. I think that's it, huh? Unless there's draw free body diagram of each of the blocks. Yeah, looks good. And maybe the only thing I would do is split up this MG over here so that it is pointing one in this direction and one in this direction. I think that's nice. Maybe I would just do little dotted lines in a different color and then use some SOHCAHTOA. And I think this angle theta here is the same as this angle theta here because this angle doesn't make sense. So hopefully that's good. And that gives me 3 marks. Amazing. That was so much easier. So you know what? I'm just going to put a little ba-bing. Actually, let's do it in green, a little bit thicker. Ba-bing. Let me put a little thing like this. So this is done. This little box and scratch out thing means it's done. Find an expression in terms of mm theta for the minimum coefficient of static friction such that the system remains in static equilibrium. Damn! Okay, so how do we do this? Static equilibrium. So basically the force of friction, and they didn't say the force of friction previously, but we're going to add a little force of friction over here. Force of friction, which is mu static times the normal force. So the force of friction, the force of static friction has to exactly equal, or it has to be bigger than the tension plus the x component of the mg. So this is mg, and is it cosine theta? It is opposite, so it's sine theta. So the force of friction has to be bigger than the tension here, and the tension here, this tension is exactly equal to mg. So the force of friction is equal to mg plus mg sine theta. And what they're asking us is find an expression in terms for the minimum coefficient of static friction such that the system. Okay, so check this out. If the force of friction is exactly equal to this stuff over here, this stuff, then the thing is like just very slightly in equilibrium. And if this force of friction is greater, then the thing is going to stay there, right? It's stuck. So if they're saying find the minimum, then I'm just going to do an equality here and solve for this. So force of friction is equal to mu normal force. And the normal force in this case, the normal force is pointing up here. So the normal force is exactly equal to mg. And then here we have cosine theta because it's the adjacent. So we have mg cosine theta. And now we isolate for this. So basically we have mu s is equal to mg plus mg sine theta over mg cosine theta. And I think that's the final answer. And damn, I feel good about this, guys. I don't know if this is right, but like doing this on the exam, I would just be like geeking out because that was way easier than the multiple choice. I'll be real. And that's it. I'm just gonna move on. I don't care. We're gonna double check later if we have extra time, but we're just gonna zoom through this because there's so much more important stuff we need to do. By the way, if you don't understand my solutions to any of this, the point of this video is for me to just throw kind of my random like brain thinking onto the page to show you guys how I think during a final exam and to give you some ideas like how to run through this if you're completely scared. Like, don't be so scared. But if you do have some questions, drop a comment, be like, what did you do on this problem? And I'll try to give a reply. Or you could just copy paste this problem into Google, see what they say. They're probably going to have a good answer. Or any free AI, just copy paste this problem. If you don't have a solution manual, that's a good strategy. But also don't rely completely on AI. AI can make mistakes. 17, 10 marks. So we just got 10 marks from number 16. That was amazing. A cylinder of mass m, length L, and radius r rolls without slipping on a flat surface. Ooh, this is scary. V, center of mass, is equal to 5 meters per second. The friction between the cylinder and the flat surface is negligible. It then reaches a rough inclined surface, 30 degrees, with mu k is equal to 0.5. How far up the inclined surface will the cylinder roll? For the cylinder, ICM is equal to 1/2 mr squared. Take the resistive force of the cylinder as mu k n, where n is the normal force on the cylinder. Take G. How far up will it roll? Is this a kinetic energy kind of problem, or is this a force kind of problem? Mm. Kinetic energy deals with mass and velocity. And we have like let's just circle all the things we have here in pink. So we have a velocity. This is the velocity originally over here. Cylinder of mass m, length L, and radius rolls without slipping on a flat surface with this a friction between the cylinder and the flat surface is negligible. Okay, so there's no friction here on the flat surface. It then reaches a rough incline of, and they give us a theta. So this theta is going to make an appearance somewhere. And then they give us this, and they also give us the force of friction. So the force of friction has to be somehow used. And they also give us the moment of inertia. So the reason I'm thinking of kinetic energy is because I feel like if you want to figure out what's happening here, all you can do is find the kinetic energy, which is 1/2 the mass of the thing times v center of mass. And if you find that, you know how much energy this thing has. You can't really find any force related to this. So I don't know, like I'm not automatically thinking about forces here. But okay, we have a center of mass and we have a theta and we have a force of friction. Let me just go back and see what equations have the moment of inertia. Here's the moment of inertia. There's a few equations that I wrote. This one. So there's this. Angular momentum, I don't think this is neat. This is useful because we don't have an omega. Let's check down here. Ooh, peep this. So kinetic friction, kinetic energy rotational. We have an I, oh, but here we have an omega again. I don't like that. But we also have this torque, I, and then an alpha. Oh, but check this out. Check this out. We don't know omega, huh? We don't know omega. But we do have an equation over here which relates omega to V. It relates omega to V, but is V the V at the center of mass? I don't know. I'm going to skip this question and read the next one, see how we feel. Hopefully this is going good. We have 43 minutes. Damn, this might actually be 3 hours, guys. Tarzan with a mass 70 kilograms swings from the rope. Ooh, this is going to be a tough one. Length 5 meters, which is originally at an angle 60 degrees with the vertical, and grabs Jane 50 kilograms at the bottom of his trajectory. When the rope is vertical, what will be the maximum angle the rope makes with the vertical after the two of them swing together? What would be the maximum angle? So theta is going to be less than 60 degrees, right? Because this guy picks up Jane, they weigh more, so they don't have enough energy to, well, yeah, the energy that it takes to bring a greater mass at the same angle is going to be more than what's provided. So is this a energy problem, or is this, how can we solve this? So it is a circular motion kind of problem because we have a radius, right? He has a rope 5 meters, so the radius is equal to 5 meters and 70 kg. With a mass 70 kg swings from the top. Let me just check very quickly if there's any interesting equations related to rotation. I don't know, there's torque. Can we use work? I don't know how to solve this one either. I'm gonna just read the next because I'm getting a little spooked. Want to do one as easy as the first one over here, 16. A bullet of mass 200 g is shot with v 100 meters per second toward a block of mass 2 kilograms that is placed on a frictionless table. The block is connected to a rod of negligible mass and length 2 meters, which is pinned at point P. The bullet, which is shot perpendicular to the rod, enters the block and becomes embedded in it. The system rotates about P with an angular speed omega. What is omega? Oh my goodness, what are these problems? So omega, what does this equal? We are given a V over here. We're given this 200. We're given this thing of length L, this thing mass. So what's going on here? So a bullet of mass 200 is shot with 100 meters per second toward a block of mass 2 kilograms that is placed on a frictionless table. The block is connected to a rod of negligible mass and length 2 meters, which is pinned at point P. The bullet, which is shot perpendicular to the rod, enters the block, becomes embedded in it. Then the system rotates. This one feels good, guys. This one feels good. Let's go. Okay, check this out. If we know V and R, we can find omega using this equation. Check the equation sheet. So we're looking for omega. So omega is equal to V over R, which is equal to V over 2 meters. And what is V in this case? V is the speed of the block and the bullet together. And I think we can use conservation of momentum here. So momentum of bullet is equal to, the bullet is 200 grams. We got to convert grams to kilograms. So 1,000 grams is 1 kilogram. So 200 grams is 0.2 kg times 100 meters per second. This is the momentum of the bullet. Momentum of the block is equal to 0. And then P final is equal to their mass together. So it's 2 kilograms, so 2.2. 2.2 times V final. So this V final is going to be the V that goes into our equation. Amazing. Wait, does this make sense? Let me peep. So I have 100 times 0.2. This is 20. And then 20 kilogram meters per second. And then we divide this by 2.2 kilograms. And we get let's round it to 9.1. So we get 9.1 meters per second over 2 meters. The meters cancel, and then we get something over seconds. But is it going to be radians? Is it going to be degrees? I think standard, we're going to use degrees here. You know what? I'll just keep it radians. I don't know. I'm a bit confused with this. But let's do 9.1 divided by 2. This is omega is equal to 4.55. 1 over seconds. So then is this radians? Is this degrees? Is this revolutions? I don't think it's revolutions. I don't think it's degrees. I think it's radians. But you know what? I'll just put these and then put a box radians. But keep the units like this, 1 over seconds, because that's how the units work out here. Meters cancel, and you just get 1 over seconds as the units, 4.55. So I think this is good. And I think this is answered, so I'm not going to look at this again. So it looks like we've answered 2 out of the 6, and then 2 are a bit confusing. Let's take a look at the last 2. We're making all right time, all right? We're 1 hour in, we've almost gone through the whole exam. At least we've read the whole exam and we've solved some problems. I think we're chilling. Bob wants to do Michael Jackson's anti-gravity dance move. This is sick. I love this problem already, because Michael Jackson's Pimp, King of Pop, where he leans forward while keeping his body fully straight. Alice helps him by doing the move by holding a massless, invisible string tied to his back. I don't think he did it this way. He did it by using shoes with a little groove in it, and there's a nail that went in the shoe and held it. Because I saw some patent that Michael Jackson made with the shoes, but I'm not sure. Maybe they did use strings, but if you watch the Smooth Criminal dance video, there's like 50 motherfuckers doing this. So I don't think they have like 50 invisible strings. Things are going to get tied up. I think they use the shoes. But anyway, don't get distracted like this in the exam. Alice wants to help him do the move by holding a massless invisible string. The string is horizontal. Model Bob is a uniform straight rod of mass 50 kg. Alice as a wall. See the figure. If the coefficient of static friction between Bob's shoes and the floor is 0.5, what is the tension in the rope? What is the minimum value? Bob does not slip. Damn, this is a crazy one. You know what? I feel like this problem, I'm just going to spend so much time drawing little things, so I'm just going to read 21 as well. We're going to do both problems together, I guess. A block of mass 2 kilograms is on a frictionless surface connected to a light spring with a spring constant K 100. Let me actually just outline these little numbers that we have, because this is probably going to be important. The block is released when the spring has natural length. Okay. Neither stretched nor compressed. All right. If the incline angle is 30 degrees, what is the maximum elongation of the spring? What is the speed of the block sliding down when the spring is stretched 5 centimeters? I think this problem I can do faster than the Michael Jackson one, so I think I'm going to spend some time on this one. All right, let me visualize what's going on. A block mass 2 kilograms is on a frictionless surface connected to a light spring. with the spring constant this. The block is released when the spring has natural length. The block is released. If the incline angle is 30 degrees, what is the maximum elongation? Oh, okay, so you hold the block when the spring is neither stretched nor compressed, and then you let it go. What is the maximum elongation of the spring? Okay, automatically I remember F spring is equal to minus K delta X. All right, what is the maximum elongation of the spring? This is what we're looking for, maximum elongation. And we have K, so what we need to do is find F of spring. But what is F of spring? So if F of spring is the spring pulling it this way, then the block is also sliding down here with F of block. I don't know, right? Because if we draw a little free body diagram, the block has an mg down here and it has a normal force up here. And there's no friction. I think we're vibing with this. So we can basically break down this mg into its components, and the only component we're interested in is this x component, f mgx. And this angle theta is 30, so it looks like the opposite. So mg opposite sine 30 degrees is equal to fg in the x direction. mg, and we have m, and we have g. And I think fgx is exactly equal to f of spring. So f of spring is equal to fgx. That means we can plug this in, and oh man, we're cooking. We're cooking today. I think this looks right, but I probably am gonna look so goofy if all of this is incorrect. But guys, this is what I did on my final exams, and I did amazing. Well, yeah, I failed a few, but overall I had some solid grades. So sine of 30, it looks like everything here is known. Is equal to minus K, which is 100. 100. I'm going to keep the units Newton meters times delta X, which is what we're looking for. Beautiful. Let's calculate all of this. So we have 2 times 9.8 times, I need to pull out a sine over here. Sine of, is my shit in degrees? It's in 30. Oh. Okay. So you get 9.8. 9.8, and the units here are kilograms meters per second squared. And then we divide this by minus 100 newtons per meter. So if we do 9.8 divided by 100, we get 0.098. We have to carry this minus sign. And then the units here are a bit strange. So let's do some unit analysis just to make sure we're sane here. So kilograms, wait, let me use a more nice to see color. Kilograms meters per second squared, and then we flip and multiply this, so we have meters here and newtons here. So these meters combine, and I know from Newton's second law, F equals ma. F is in newtons, m is in kilograms, a is meters per second squared. So I'm just going to replace kilograms. I'm going to combine these meters into meters squared. On the bottom we have second squared. And then here we're dividing by 1 Newton, which is kilograms meters per second squared. So we have 1 kilogram on the top. Wait, let me do this color. 1 kilogram on the top, 1 kilogram on the bottom. 1 mass, 1 meters on bottom. Oh, wait. Let me rewrite this a little bit more clean as well. So we have kilograms meters squared per second squared. And then we have the seconds goes to the top, and then the kilograms stays here with the meters. Okay, now it looks a little better. Kilograms cancel. One of these meters cancel with one of these. These cancel with these, and we get meters. Let's go. Okay, delta X in meters. Boom. This one over here. Delta X. What is the maximum elongation of the spring? It's negative 0.98 meters, or you could just say 0.098 meters. Forget the negative. The negative is just how we define the coordinate system. So the spring starts here. The maximum it's going to elongate is this delta X that we found. So it's going to elongate here. Maybe the block is going to go a little up. It's going to go a little down, but it's going to like... Ooh, I didn't think about this. You know what? No time to think about it. We're like 1 hour in, so I'm just going to leave it as that. What is the speed of the block sliding down when it is stretched 5 centimeters? Oh, man. So you know what? I'm gonna take all of this, resize this, put this over here. And whew, how do we do this? So okay, I think this one is done here. Color this, box this out. What is the speed of the block sliding down when the spring is stretched 5 centimeters? Okay, so now we have some new stuff to work with. I'm still gonna write F spring is equal to minus K delta X. And then here we have minus 100 newtons per meter. And then they're giving us stretched, when the spring is stretched 5 centimeters. So that's going to be the delta X, 0.05 meters. I like keeping everything in meters. So that's going to give us a force on the spring. This is confusing. What is the speed of the block sliding down with the spring? I'm not sure about this one, guys. But if we use the spring equation, then we can just pull the force that this block feels right now. But is that useful? How are we going to find speed? Let me check if there's some kind of equation with a spring that I can pull a V out of it. So this is the equation I've been using, but if I use this, and then I plug this F into F equals ma, then I can only solve for A here. But then maybe I can use something like this, huh? The block starts from rest, it accelerates, but we don't have the time. But maybe we can use this. This. Oh, can we use that? So check this out. Check out how I'm thinking here. We got the spring, right? We have K and we have X. So from this, we can get the force that the spring is creating on the block. So the block feels a force. I don't know exactly how to explain this, but the block feels a force. Plug this force into F. We have the mass of the block. We can isolate for A. We have the A of the block at that given moment. They're asking us for the speed, right? And this is a linear kinematics thing. The block is just moving in a straight line on this little ramp here. And then I look through these equations and I look at what I have. So let's say the block starts at rest, right? So this initial thing is going to be 0. We have 2, we have A, and then delta X could be the same delta X as given to us here. Maybe, I'm not sure. Then we can isolate for this. You know what? I'm just going to do that, and that's the only idea I have right now, and I kind of want to move to the other questions. And we're about an hour in, so this is the last problem of the exam. We don't have to read new problems, we just have to go and revisit other problems. So I think that feels good to me. So let's write this. V final squared minus V initial squared is equal to 2A delta X. Is this the right equation? 2A. Yeah. So what do we have here? We have F of the spring, which is minus, I'm not going to put the minus in my calculator, but I'm going to do 100 times 0.05. This is 5 newtons, minus 5 newtons. And then this we can put into F equals ma perhaps, but the question is, do we combine it with the force? So this is the force just the spring is providing. This is why I'm a little confused and I'm kind of just throwing an equation and trying to solve the problem, but the block is at this stage, right? After it is extended 5 centimeters. Right? The spring is pulling it this way, perhaps. I don't know which way it's pulling. It's probably pulling this way, but the block still feels an mg this way. So to this, do we add a component of mg in this direction? That's going to mess us up. Because if I isolate for this A, I can then put it in here and I can isolate for our thing, and that's going to be the final answer. But my question is, do I just put F of spring in here? Or do I also add or subtract or whatever? Like maybe the force of the spring is minus here, right? Because we have a minus here. Peep this. So do I add to this F, G in the X direction? This is my question. And you know what? If I'm really spooked, I'm going to do both. And I'm going to do both live. Because I don't think it's too much work. We're going to be vibing. So check this out. We have minus 5 newtons. And we divide this by the mass of the block, which is 2 kg. 2 kg. And because of unit cancellations and stuff, this is 2.5 meters per second squared. Beautiful. So if we have minus that, then we can also do mg, and then this was sine 30, sine 30 minus 5 newtons over 2k kg, 2 kg. So the mass of the block is 2 kg times 9.8 meters per second times sine of 30. So this is just 9.8. And then we subtract from that 5 and we get 4.8. Huh, this is actually kind of nice because 4.8 divided by 2 is 2.4. Oh, this makes me feel good because we had a dilemma, right? Do I put this or do I just use this? So I just did both and it looks like, oh no, it's a little bit off. This is 0.4. So it doesn't really matter. Unless my math is completely wrong and the answer is found a completely different way, it don't really matter. We're going to use this. And now we have V final squared is equal to, because V initial is 0, we're going to assume 2 times, let's use 2.5 meters per second squared times this 0.05 meters. I have no idea if I'm doing this right. Let's try it out. So we have 2 times 2.5 times 0.05. This equals 0.25. And then we square root that. Square root 0.25 is V final is equal to 0.5. And then this is meters per second. All right, maybe this makes sense. Maybe this makes sense, and I'm gonna put this, and you know what? I'm chilling. So it looks like we have 1, 2, 3 out of the 6 problems solved. I'm just gonna go back and sweep through all of the multiple choice. So they hit the ground at the same time. I think I'm good with this one. A projectile that is launched horizontally goes down 1 meter in the y direction after going forward 50 meters in the x direction. What is the initial velocity? Sorry, just gonna take a little break. It's been 1 hour. I think I've made good progress for 1 hour. And I'm sorry if you're not learning too much from this video. I thought it would be helpful to show you guys how I think on these exams. And it might be a little sporadic, it might be a little insane. You might have no idea what I'm saying, I'm not too sure, right? Because I'm a little removed from your guys' position. Like, I have studied this class several times, I've helped people with it, so I have specific ways of thinking about it. But I thought me just showing you and speaking about how I think about this stuff, maybe it's going to be helpful, and you can do the same thing. I was hoping you guys can absorb something from this and apply the same stuff to your problem-solving strategies. But anyway, let's stop getting distracted. Sometimes it's good to just take a few seconds to breathe, but then get right back into grinding because you have a limited amount of time, 3 hours. So let's peep this. A projectile that is launched horizontally goes down 1 meter in the y direction after going forward. So first it goes 50 meters, then it goes, and I guess it's at the same time. Take g to be 9.8. What is its initial velocity? Okay, peep this. So it goes down 1 meter. So using this equation, x final is equal to x initial plus vit plus 1/2 at squared. X final is equal to 1 meter. X initial we can say, sorry, this is the y. This is I'm talking about the y over here. So maybe it's good to write this. This is y final, y initial. So y initial, it drops by 1 meter. Maybe a minus sign here. Not sure. We'll see if that minus sign is useful, but we're going to say it starts at 0. The initial velocity here is what we're looking for. So this is the initial velocity in the y direction. A projectile is launched horizontally, so the initial velocity in the y direction is 0 plus 1/2, and then this g, I think, has to be negative here. I think that's what makes sense. Negative 9.8 meters per second squared, and then this is t squared. So what am I doing here? Why I'm just isolating for time? I don't know if that's too useful. Oh, maybe it is. Maybe it is, bro. Okay, so I just used this equation, the kinematic equation, which is projectile under constant acceleration in the y direction. I have minus 1 meter, so I have 1, and then I'm just going to isolate for t. So 1 times 2 to bring that 1/2 on the other side, divided by 9.8, and then the minus signs cancel. And I get 0.204. 0.204. Square root of 0.204 is equal to 0.45. Damn, it moved 50 meters in 0.45 seconds. So its initial velocity, and you're only finding initial velocity in the x direction. And it traveled 50 meters. Here we go, guys. V in the x direction is equal to 50 meters over 0.45 seconds. Let's hope one of these answers is it. 50 divided by 0.45. This is going to be 111. Oh my god. We are cooking, guys. I feel so good seeing one of these. Even if it's wrong, fuck it. So now we're good with this. So you know what? I'm just going to put green over here just to make sure this is checkmarked. Green over here just to make sure this is checkmarked. So I don't want to look at it again. I don't want to stress out. This one. This one is tough. 1,000-kilogram car drives up a semicircular hill with a radius of 10 meters. What maximum speed can the car go over the hill without leaving the surface? Jumping. Take G to be 9.8. So you guys have been on a hill. If you drive really fast, you're going to like leave off. So you have to drive slow enough. But if you drive too slow, you're not going to jump off. So there is a speed at which you are driving really fast and you're just about to leave off, but you're not. And then if you go just a little bit faster, you fly off. So how do we figure this out? Last time I got was 10 meters per second. How did I do that? Oh, centripetal acceleration. Centripetal acceleration. So you're going around in a circle, right? Because you go a semicircular hill. Semicircle means half of a circle, right? Semicircular hill radius, and it gives you a radius. So for sure, automatically I thought about this equation because there's a radius, there's a velocity. This velocity is the velocity that you are experiencing at this radius point. What maximum speed? And here is the v. And then they said take g to be 9.8 meters. Sometimes they put this to confuse you, but in this case, I don't think they're putting it to confuse you. So I feel like this g could be put here or something like this. But you know what? This, I think, is pointing inwards. I think it is pointing inwards. I'm not too sure. So round your answer to the nearest integer. That's what they said for this one, right? Round your answer to the nearest integer. Okay, I'm going to think about this one a bit, but I'm just going to go to the other ones and see. Block with A, mass M, slides on a frictionless horizontal floor. It then collides with block B, mass M, which is at rest, and completely sticks to it. What percentage of kinetic energy of the block A converts to kinetic energy of the two blocks after the collision? Kinetic energy, what percentage? What percentage of the kinetic energy? Okay, I'm just going to erase this because I have a mental picture in my mind of what's going on. I have a mental image of what's going on over here, but I want to figure out what this percentage thing they're talking about. So what percentage of kinetic energy B converts to kinetic energy? So Ka over Ka plus B, this is a percentage times 100%. This gives us a percentage. So it's either this or you flip these. I'm not sure, but something like this. Like percentages are always a ratio. What is your grade out of how many questions there are in this? So how many marks are in this? If there's 100 marks and you get 40 marks, your percent is 40 divided by 100. You're not going to do 100 over 40. But in this case, we're talking about kinetic energy, and I'm a bit confused. So there's a ratio here. And Ka is equal to 1/2 m a, right? M, and then v squared. So we have this, but we don't have v after. It then collides with block B with mass M, which is at rest. So Ka plus B, it was at rest. So now the masses are 2m. This is a little different here. This is the thing that might give us a 50% or something like that. And completely sticks to it. What percentage? So where does the velocity go? Like they don't give us a velocity. So if I put v squared here, and then I do, let's just do ka over ka plus kb. 1/2 mv squared over 1/2 2mv squared. So what we get here is the 1/2 cancels with the 1/2, the m cancels with the m, the v squared cancels with the v squared. We get 1 over 2 times 100%. So this is 50. And if we flip that, it's going to be 2 times 100% is 200. So I think it's this one, guys. I think it's 50%. Yeah. That makes sense if the velocity is the same. So you know what? I'm not going to spend any more time on this. Let's check this one again. 100 kilogram, 1,000 kilogram car drives up similar circle. What is the maximum speed? You know what? I'm also going to draw a little bit because I noticed like when I draw some stuff, like things work out to be a bit better. But I do think this centripetal acceleration equation is going to be used. So let's say you're right here. This radius 10 meters and your car is here going velocity v. And what is the thing pushing you up? Out. There's something that's pushing you up. Otherwise, why would your car fly up a little bit? And then there's something pulling you down. So if this thing pushing you up is bigger than this thing pulling you down, then you're going to fly up. But if this thing pushing you up is a little weaker than the thing pulling you down, then you're not gonna fly off. So what are these things? I'm trying to think, but I know we got to use this somehow. I'm positive, guys. Well, I'm not positive. I could be wrong about everything. Guys, in these scenarios, if I have an equation that I'm kind of interested in, and I have 4 options that I'm completely unsure about, and I have this, here's a strategy I would use, and I think this is going to give us a final answer. Peep this. So, I'm going to find AC for all of these guys, right? And it's pretty easy because we have the V and we have the R. So I'm going to have 5 squared over 10, and then so on and so forth. 10 squared over 10, whatever. So peep this. 5 meters per second times 5 divided by 10. This is 2.5. And then this is meters per second squared. You can do the units if you're interested. The next one is 10 times 10 divided by 10. This is just 10 meters per second. And it says round your answer to the nearest integer. Okay. If we get, wait a second. 9.8. What is the maximum speed your car can go? So maybe the maximum speed is 9.8. Yeah, guys. Okay, I think the answer is 10. But let's do the other ones. 14 times 14 divided by 10. This is 19 meters per second squared, meters per second squared. And then 20 times 20 divided by 10. This is 40 meters per second squared. So here's what I did. I just used this equation. I plugged in the speeds that they give us in the questions, and I divided by this r over here, this r. The mass of the car doesn't matter, I think. And then what I found was, okay, you get an acceleration value, acceleration. And then they tell you this. So if this acceleration you get from going this speed over a circle of radius this acceleration, if it exceeds the gravitational acceleration of Earth, then you're going to fly off. I think this is how it works. And then it says round your answer to the nearest integer. So if you're going 9.8 meters per second times 9.8 meters per second divided by 10, you get 9.6 meters per second squared, and then you round that up to 10. So hopefully that makes sense, but I think this is the answer. You can go 10 meters per second. Because if you plug that in here and divide by this, you get this, and this thing is the only one closest to 9.8 meters per second. This is clearly a slow speed, you're not going to fly off, and 19 is clearly bigger than this, so you're going to fly off completely. I don't know if that made sense. This is me just kind of randomly making some like crazy jottings on the exam. But now we got the first 4 done, and we can move on to 5. In car accidents, how do airbags save the passenger's life? Oh, they decrease the change of momentum of the passenger compared to the car with no airbag. I don't think so. They increase the interaction time, which the passenger is brought to rest and hence decrease the force applied on the passenger. Airbags do not affect the force applied on the passenger. I think that's true. So I originally guessed this too quickly. They only allow more time for the body to adapt to this force. They only allow more time for the body to adapt to this force. You know what, guys? This is going to be a guess. I don't like guesses. I don't like guesses at all. But this one is going to be a guess. I'm putting that one because something about it makes me feel good. Something about decrease the force applied to the passenger doesn't make me feel good. And then this one, do not affect the force applied. They only allow for more time for the body to adapt. So I think this is true because the force that you feel is always going to be the same if it's the same exact car crash. So this is increased interaction time. This also says increased interaction time. So they're very similar, but this one says it decreases the force applied, which I feel like is kind of true, but I don't think it is. I think they're trying to finesse you. And then here they say the force, airbags do not affect the force. They only allow for more time. So I think this is it. I don't know. In figure skating, Alice is spinning. You know what? This one, I'm not even going to look at it anymore. I think it's good. Let me know if it's not. A ball and a box are placed on a frictionless inclined surface. If we let them go at the same time, the ball rolls without slipping. The box slides down the inclined plane. Which one will have a larger velocity center mass? Okay, so yeah, I think both of them have linear kinetic energy, but the ball has also rotational kinetic energy. So more kinetic energy means faster, and I think that's enough to just mark this one off and not look at it anymore. But again, double check. Please don't take my word for it. I'm just kind of zooming through. Like I said, I'm not a super genius. I'm not an AI computer. I'm not even a professor of this class. I can get things wrong. This is just like a proof of concept showing you guys how I go through exams. And so far, it looks like we've done almost all the multiple choice. We're left with, I don't know, half of them-ish. 2 bullets. You know what? I'm not going to look at this one too because I've seen that Veritasium video so many times. I know this is correct. Asterisk on that one. Bar magnets. Ooh, this one. I'm going to skip this one. Oh man, we skipped so many here. These guys are going to take so long. Let's go to the long answer real quick and just take a gander of what's going on. So we got the Michael Jackson problem, we got the swinging problem, we got the incline problem. It's not looking too bad. We got 3 long problems, and we got a bunch of multiple choice. And we've been working for an hour and a half almost. Honestly, we're in a good position, guys. I think we're vibing right now. Bar magnet of length L, mass M is spinning about its center of mass with a constant angular speed. We slowly push. You know what? What I'm going to do here is find the new moment of inertia. And if the torque is the same, because no force is applied, and the moment of inertia is the only thing that changes, then omega is the only thing that can change. And from that, I think we can solve the problem. Okay, so peep this. This is what I'm thinking here. I remember torque is equal to I omega. Is this true? Or I alpha? Oh, damn. I think it's I alpha. Let's check. So torque is equal to I alpha, and angular momentum is equal to I omega. Angular momentum. Angular momentum is conserved. Okay, I was either thinking about torque being conserved or angular momentum being conserved, but angular momentum is king. Conservation laws are king. So peep this. Angular momentum is equal to I omega. Angular momentum before is equal to angular momentum after. Angular momentum is conserved. So the only thing that can change I before times omega is equal to I after and omega prime. So we can solve for omega prime. It's equal to I before omega and then I after. Okay. Oh man, I feel good about this. Let's go, guys. I'm actually cooking. Okay, let's look at this. I before is 1/12 ml squared times omega, right? And L, by the way, here is the length of the thing, not angular momentum. And now the new moment of inertia changes. So it's still going to be 1/12 because it is a bar magnet. So before, the bar magnet was like this, right? It had the moment of inertia I, Cm that's given to us in the problem. But then it combines to a new one like this. But it just looks like a bigger bar magnet. So it's going to be the same, except the mass is going to be times 2, and the L is going to be times 2 as well. Oh, this is beautiful. So let's cancel all these. Cancel this, cancel this, cancel this, cancel this. Cancel this, cancel this. The square applies to this. So we have on the bottom 2 times 2 squared. So 4 times 2, 8. Omega over 8. Oh, baby, let's go. It's this one right here. Let's go. Hopefully that's okay with you guys. I don't know. Conservation of momentum helped me out here. But like I said in the equation sheet video, find an equation that has the things that you're looking for in it, see what changes, and the big thing that changes here is moment of inertia before was this thing, and moment of inertia after is these two bar magnets combining, and it's the same equation except the mass doubles because now we have 2 bar magnets, so I put 2m in here, boom. This is just the new m, like m after, you could say after. And then this is the new L, you could say L after. And then I used conservation of angular momentum. So angular momentum before is equal to angular momentum after. And then I just take this side of the angular momentum before is equal to after. So this equation here, this one here is basically conservation of angular momentum. Then what they're asking us for is find omega prime in terms of all this other stuff. So I just solve for omega prime. And I have this before, which is given to me here. Omega is allowed to be part of the problem. It's shown over here. And omega after is the thing I calculate over here. You can see a bunch of the things cancel over here, boom, boom, boom. And then we get one of these answers, this one. So I think we're chilling with this. Oh, and that makes me feel so good. Look at all this. We're zooming. I don't know if any of this is correct, but just getting some kind of validation that we're on the right track makes me feel good. I did not study chapter 15 on simple harmonic motion, so here I think we might be screwed, but the problem with this question is there's a t here, which is the period, and the period is currently unknown unless we find a way to solve for it. So here we have period, but this gives us mass and k and 2 pi, and I don't think mass and k are given to us in this problem. A mass spring system. Oh. Oh, but check this out. Check out this equation. I'm going to write this equation exactly like this, and then I'm going to write this, because look at this. Inside here, we have an omega, we have a t, and we have this phi. I don't think in our problem, we have this phi. No, we don't have a phi. We just have this. And check this out. We have this 2 pi times a t. So here we have a t, and what's multiplied in front of the t? It's the omega. So omega is equal to 2 pi, I think. Do you guys see what I'm saying? So I'm going to write this down. So x of t from the equation sheet is equal to a cosine omega t plus phi. And in our problem, this plus phi does not exist, so we just have omega t. And in our problem, what we have is 3 cosine 2 pi t. So now we can make a connection here. This t is just exactly shown over here. This a is exactly shown over here. So this omega must be 2 pi. There's nothing else it could be. So if omega is 2 pi, now we can maybe solve for t, because look at this. We have omega. We know omega is 2 pi, and then t over here. So if omega is equal to 2 pi, then you cross multiply. So this t goes to this side, and this gets divided onto this side. So t equals 1. Oh my goodness. Is that all we need? And also they give us v over here. Look at this. V is equal to omega a sine omega t. Negative omega a sine omega t. Negative omega a sine omega t. Wait, which problem were we at? We were over here, yeah. So what we're asked for the velocity. So in the velocity equation we have negative omega a sine omega t. So we're looking for velocity, and we have vt omega. So now we can like build this equation. Vt is equal to minus, and omega we learned was 2 pi, and this a is 3. And now we have sine omega is 2 pi, And now we learned that T is equal to capital T over 4. And we learned that capital T is 1. Boom. So now this is literally just plug and chug. 2 times pi times 3 times sine of 2 times pi times 1 divided by 4. And this, I think, has to be in radians, because there's pi in there. I'm going to convert that to radians. If you convert it to degrees, you get 0.51, which is not any of the answers, but if you convert it to radians, you get 18. So I get V at T is equal to T over 4 is equal to 18.85. And now I'm just going to check what 6 times pi is, and that is 18.84. That's clean. But wait, we have a minus sign right here. Boom. So I think this is the answer. Minus 6 pi. So here's what I did. This is actually a crazy problem. They give you this x of t, right? I pull the equation from the equation sheet that looks exactly like that. Then I match a, it's 3. I match omega, it's 2 pi. And this omega equals 2 pi is super important. It's what tells us what this t is. So if omega equals 2 pi, we go to this equation, omega equals 2 pi, and then remove this, use this, and you can see that t is equal to 1. So now we have something that we can plug in here. Which problem was this, man? I keep getting lost. We have basically 1 over 4, and they're asking for the velocity, right? So I take the velocity equation, I match everything again. Here's a, it is 3, right? There's a minus sign. I have a 2 pi, which was the omega, and inside I have omega t, and we already learned omega was 2 pi, and this t is given to you. It's capital T, the period, over 4, and we learned the period was 1, so 1 over 4. Now I just plug everything in here, and I get this. I switched around between radians and degrees. If you see 2 pi inside a trigonometric identity, most of the time you have to put shit into radians, because 2 pi is radians, right? So keep this in mind. This is a little tidbit, but it's important. So we have a minus this, and then this 18.65, it's 6 times pi, exactly this. So hopefully that made sense, and now I feel amazing. You guys see how just like reading through the problem and then go back, you can kind of piece things together. All of these done, 11, 12, 13, 14, and 15. Oh man, we're doing good. I think I'm going to solve all this, but I think it's going to take me 3 hours. Hopefully this video is enjoyable. 12 kilogram block on a horizontal frictionless surface is attached to a spring, force constant 800 newtons per meter. The block is initially at rest at its equilibrium position. When a force, this one was confusing. What is the speed of the block when it's 13 centimeters from equilibrium? Okay, I think we did some problem similar to this. It was this problem here, huh? Was it this? Yeah, we did something like this. The speed of the block, we use this. Okay, I think we could do the same thing here, huh? Maybe we can. So what is the speed of the block when it is 13 centimeters from equilibrium? So the delta x is equal to 13 centimeters, which is 0.13 meters, right? Mass is 12 kg, and then k is equal to 800 newtons per meter. So the most important thing is I'm just isolating the numbers we have, but then this force, this P, is the confusing thing, right? Because if we use F of spring is equal to negative K delta X, we can plug negative K in there, we can plug delta X in there, but then we're stuck with the question where before we had sum of Newton's second law, A, we get A, we isolate for A, right? The acceleration at a specific point. Then we use this equation, V final squared minus V initial squared is equal to 2A delta X. And we have delta X, we have A, we can find for the final velocity there. Does that make sense? But when you do sum of Newton's second law, I think what's happening here is it's P minus force of the spring. Does that make sense? You know what? I'm gonna plug all these numbers in, see if we get something, and then I think we're gonna be chilling. So let's see here. I'm gonna do this in a different color, pink. So we have 80 newtons. 80 newtons minus K. So K is 800 newtons per meter times 0.13 meters. This is 104. 104 newtons. So this gives me, oh, it's a negative. That's strange. I don't like that too much, but my mental math here is not the best. We'll just use a calculator. 80 minus 104. This is minus 24. Now we can use this minus 24 into Newton's second law. So minus 24 newtons divided by, what is the mass? 12 kg. 12 kg is equal to A. So 24 divided by 12, is it going to be just 2? Bruh. My mental math cooks, or it gets like literally obliterated when I'm in a final exam. So we get minus 2 or plus 2. I don't know. The minus sign freaks me out a little bit here. Meters per second squared. So that's the acceleration. Now, the initial velocity we can take as 0. So we have the final velocity is equal to the square root of 2 times 2 meters per second squared. This is why I'm spooked about the minus sign, because when you remove this square, you square root over here. And if you have a minus sign in the square root, something is wrong. So I just removed this minus sign just to make the math work. And then here we can just put that 0.13. 0.13 meters. So meters, all the units work out, and it gives us meters per second, which is the velocity. So let me do this. 2 times, actually, let me do square root. 2 times 2 times 0.13, and I get 0.36. That's none of the answers. Did I miss something? Did I miss something? A block is initially at rest at its equilibrium position when a force acting parallel to the surface is applied to the block as shown. What is the speed of the block when it is 13 centimeters from its equilibrium position? So the block is initially at rest, which means that VI is equal to 0. So we're looking for V final. And I think we are using this equation, but you know what? Okay. I thought that sum of Newton's second law, the sum of the forces, is going to be this P minus this Fs. But I feel like this P is messing us up. I feel like it's useless because the speed of the block, like, this problem makes no sense. Imagine you have a spring like this, right? And this. You pull this here, and then this thing extends 0.1, it extends 13 centimeters. What does it mean, find the speed? Do you let it go? Do you keep applying this? Like, it doesn't make sense. So what I'm going to do is I'm going to just eliminate this 80. Eliminate this 80. This 140 is now going to enter into this. So 140 divided by 12 is going to give me a new acceleration. Or 104 divided by 12, 8.66 is the acceleration. 8.66 is. So now I'm going to do square root 2 times 8.66 times 0.13, and I get 1.59. That's still not an answer. Man. You know what? Let me try 80. I'm just going to instead put 80 into this equation. 80 divided by the mass gives me an acceleration. So 80 divided by 12 gives me 6.66. Wait, wasn't that the same thing? No, it wasn't. So now I'm going to do final velocity square root 2 times 6.66 times 0.13, 1.22. Still, bro. This problem is weird. I'm thinking. I'm just gonna sit and think for a little bit. How you guys doing, bro? Like I said, I did not read any of these questions beforehand. I'm just hopping in and I'm yapping. I thought I was gonna do like a 15-minute yap session and it's gonna go easy, but Man, these final exams even, they screw me. But let's look at the whole exam and just get some like glory out of this. All of these are solved, we're good. We have 1, 2, 3. Actually, some of these I think are answered already. So it looks like we have one that's confusing. And we have another one down there that's confusing. So it looks like we have 2 multiple choice and still these 3 long answers. I'm not sure. I'm not sure about this one. And I don't know if I'm doing something incorrect here, like if I'm using the wrong equations. I feel like I'm using the right equations because there's no other equations you could use here. You have the extension, you have the mass, you have the spring constant. Let's check if there's another equation that I'm blanking out on. Where do we see the spring constant? We have the kinetic energy, or the potential energy of a spring. Interesting, potential energy. Can that help us somehow here? I don't think. I don't think it's going to help us. Whenever I get lost with this, I take the answers and plug them into my equation and see what it spits out. If it spits out something interesting, then it's cool, but I don't like this because the answers here look weird. Two times acceleration times the displacement. Alright, I'm gonna skip this one again. A disk of radius 8 centimeters rotates about a fixed axis. I think this one we did well. What is the magnitude of the total linear acceleration of a point on the rim of the disk at the... Oh, but it says total linear acceleration. This word total spooks me a little bit. Linear acceleration of a point on the rim, because total linear acceleration, like, do we have to do some subtraction or something? Like, we take this A and we subtract like AC from it or something like that? Ah, man. I don't think so. Linear acceleration of a point on the rim of the disk at an instance when the angular velocity of the disk is... At the instance when the angular velocity of the disk is 1.5 radians per second. Total linear acceleration. So, it says constant rate of... Oh. Oh, no, we're good. The thing has 8 centimeters, right? It starts from rest, omega initial equals 0, accelerates at a constant rate. So the acceleration at the beginning, the acceleration at the end, and the acceleration at every point in time all the way between this is going to be always the same, which we found to be, I don't know, I erased it, it was down here. It was some number though, which we found using those angular kinematics equations. And the final is this, for 2 seconds. So we use one of those kinematics equations. I think it was omega final is equal to omega initial plus alpha times time. So we have this, we have this, we have time. So we isolate for alpha, we get alpha. And then we just convert this to meters. This times this gives us, I think it was this. So you know what? I think I'm going to mark this one as good as well because I'm freaking out, like I want to do the other problems. And I don't want to focus on this one anymore. So we have that one left, 11, which is going to throw us in the gutter. But you know what? We can leave one. We can leave one. Everything else is completely correct. I'm going to just believe this so that my vibes for the rest of the exam are good. 2 watermelons. This one I also feel good about. I think kinetic energy here just relates to the mass if their velocity is the same, but they don't say if the velocity is the same, so that's one little hiccup, that one little guess that we have to make. 300 kilogram bird or a 300 gram bird flying along. I did conservation of Hang-Mom or Lin-Mom, linear momentum. Let me just do this again. 300 times 8 minus 10 times 30. 2100 equals divided by 310, and then I get 6.774, round that up to 6.8. This one feels good to me too. I'm gonna mark this one correct. 5 kilogram mass is suspended by a string from the ceiling. Okay, this one I think this one feels good to me. Yeah, I remember doing a little bit of this. I think it feels good. So all the multiple choice are done except this guy. And you know what? I'm gonna put a big this over here just to say like, yo, do this one. So that answers all of the multiple choice. We're almost two hours in. All the multiple choice except one is done, and all of the long answer are done except 3, which feels good. So what do we do here? What is the tension in the rope? All right, we can do this Michael Jackson one. Let's go, baby. Michael Jackson movie coming out soon as well. So here we have the string. It is feeling a tension this way. We have to find the tension. What is the tension? Tension equals question mark. Now this Bob, he is modeled as a rod. Model Bob as a uniform straight rod of mass 50 kg. So if this guy is a rod, right, and he's falling this way, it's like a torque that's being applied, right? A torque. So this torque, the whole rod wants to fall over. The center of mass, 50 is pulling here. Let's go. I think we're chilling. This is a torque problem, I think. So the torque of Bob is equal to R cross F. And the R here is at its center of mass. So how long is Bob? Model Bob is a uniform straight rod 50 kg. Alice is the wall. Bob wants to do he leans forward while keeping his body. Oh wait, they don't give us a length for Bob. This is not a torque problem because we don't have R. This is Model Bob 50 kg. Oh man, I thought this was a torque problem because we have one torque which is pulling this way at this, and then another torque which is pulling this way. So, torque Bob minus torque Alice is equal to 0. Torque Bob is exactly equal to torque Alice, and then we can, from that, find the tension of the string if we had the length of Bob. Bob wants to do Michael Jackson's anti-gravity move. While he leans forward while keeping his body fully straight, Alice keeps him doing the move by holding massless invisible string. Model Bob is a uniform rod of 50 kg and Alice has a wall. See the figure. If the coefficient of static friction between Bob's shoes and the floor is this, what is the tension in the rope? So Bob wants to slide this way, but there's friction keeping him that way. So there is a friction over here, force of friction, which is equal to 0.5 times normal, which is 0.5 times the mass of Bob, which is 50. I'm just going to write 50 kg times g. Okay, so, I don't know if that's helpful. Man, this is a tough one. What is the tension in the rope? But how does this coefficient of static friction thing help us? And what is the minimum value of theta above which Bob does not slip? We're approaching the 2-hour mark. This is not bad where we're at right now, but it's not good either. I don't know how to do this one. Let's check. Okay, we did this. Michael Jackson. Let's check Tarzan. I think Tarzan's going to be an easy one. Hopefully. Tarzan with mass 70 kilograms swings from a rope of length 5 meters, which is originally at angle theta is equal to 60 degrees with vertical, and grabs Jane, mass 50 kg at the bottom of his trajectory when the rope is vertical. What will be the maximum angle the rope makes with the vertical? So we have mass. Let me just write down all the things we have. We have mass, we have radius, and we have theta. And I guess we have g, so could that give us Fg? I don't know. Maybe this is a torque, maybe this is an angular momentum thing. Maybe it is an angular momentum thing. Angular momentum, oh, this is an angular momentum problem, isn't it? Let me double check. Angmom. So we have m, r, and theta. M, r, and theta. And do we have the force too, huh? Do we need the force? Or does angular momentum use torque? Let me check the angular momentum equation. V. Oh. We don't have omega, I don't think. We don't really know I. I don't know if this is a torque problem either. I don't think it is. So the mass of Tarzan times the radius of the rope crossed with the velocity of Tarzan. What is the velocity of Tarzan? Tarzan with mass swings from the rope of length 5, which is originally an angle, with a vertical, and grabs Jane. So Tarzan starts there and he swings down. And at the bottom he has some velocity. Okay, so here's the thing. Tarzan starts here, he swings down, and over here he has some velocity v going this way, right? If we have r, which we do, and we find this v, then we could do m r cross v and find the angular momentum of Tarzan, right? Then, exactly at this moment, he grabs her and he increases the mass. It's now the mass of Tarzan plus the mass of his girl Jane. And the velocity stays the same, I think. But then how do we get the angle? So we need to find a way to go from angle at the top. So we need to find a way of determining when this guy starts at an angle here, theta, 60 degrees, he starts here, velocity I equals 0. And he goes all the way here. What is the velocity? Velocity final equals question mark. Then with this velocity final equals question mark, if we have this and we go to velocity final here equals 0, where they reach the maximum angle, if we find a way to get the angle from here and convert it to a velocity over here, and we know how to do that again backwards, I think we're going to find a way to do it with angular momentum conservation. But I don't see a way of determining the velocity of this dude unless it is an energy conservation problem. And it must be. So he starts at a height. Oh my god, this is a beautiful problem if it uses energy conservation as well. So this guy Tarzan is at some UG over here, right? He swings down to over here, so his UG has now changed. Right? This change in UG exactly converts into the change in kinetic energy. And if his kinetic energy, initially his velocity was 0, then from the kinetic energy thing we can find his final velocity. Oh my goodness. I'm going to zoom in and do a lot of work right here. We're going to do it with a small thing here. So UG initial of Tarzan is equal to, how do we find the UG? How do we find the UG? There's going to be some trigonometry stuff going on here. So we have L, right? L is equal to 5 meters, was it? 5 meters and 60 degrees. 5 meters, 60 degrees. So his height over here is exactly this, the adjacent side of the triangle. So this, let's call this y initial. And then y final is going to be just the length of the rope, because that's when this length of the rope is completely at its bottom. So the y final is L. So actually, we can find the UG final is equal to mass of Tarzan times G times L. And then here it's going to be mass of Tarzan times G times the cosine of this, adjacent over hypotenuse. So it's going to be L, I think, cosine of 60 degrees. Does that make sense? Does that make sense? And if we take the difference between those two, oh my God, I think we're cooking. I think we're cooking with this strategy, guys. If this is actually the way to do it. I don't know if this is the way to do it, but let's try it. So U final minus U initial is equal to MGL minus, actually, we can factor out the MGLs, and then we're going to do L minus L cosine. Actually, we can factor out the L as well. L, and then we're going to have 1 minus cosine 60 degrees. Okay, let's plug this in. So this is going to be our delta U. So, mass of the guy, 70 kg. I'm not going to put units right now. I normally love to put units, but we're running short on time, and I'm going to just make sure everything is in SI units. 70 kg times G, 9.81 meters per second squared, times L, which is 5 meters, times, and then brackets, I'm going to do 1 minus, and then I'm going to do cosine of 60, and I'll put in degrees. Oh my goodness, this is a lot. .75. And what are the units here? This is kg times meters per second squared times meters, which is another this. Is that actually it? And let me check if my thing is sine of 30. Yeah, my thing was in degrees. Okay, so that number is going to equal into that. So K final minus K initial equals delta U, right? And K initial is equal to 0. So K final is exactly equal to this. So 1/2 mv squared is equal to 1716.75 kg meter squared second squared. So let me do 1716.75 divided by, or let me do times 2 divided by his mass, which is 70, and that cancels out the kg there. We get 49. Oh my God, this is beautiful. And then we square root that because the v is squared. So we get his final velocity. Oh my God, let's go. We're cooking. Square root 49, 7 meters per second. This is beautiful. This is his velocity, guys. This is his velocity. And now we can go back. Ooh, this feels good, bro. All right. This was mr cross v, which is mrv sine theta. But, and sine theta is 90, so here we can remove this, mrv, so we get 70 kg times, was it 5 meters? I keep forgetting 5 meters. 5 meters times 7 meters per second. So his angmom, oh my God. Hopefully this works, man. 5 times, I mean, I don't even know if there's a way to check. 2450 kg meters squared per second. I think that makes sense. Now we have a new angmom. So the mass increases. Actually, I'm not going to write that down. So 2450 equals the new mass, which is 70 plus 50 is 120 kg times... Okay, okay, I see. So a new velocity. So the velocity slows down because the mass increases because of conservation of angular momentum. Hopefully that makes sense. R is 5 meters, and now this is the V. V new. This is the V as soon as he picks up the girl. So V new. We have 2450 divided by 120 kg. That cancels out the kilograms on the other side. Divided by 5. That cancels out the extra meters. And then we get V new when he picks up Jane. is equal to 4.083 meters per second. Now that we have this, I know this is a big several step problem, but man, like, I don't see any other way of doing it. Okay, now that we have this new view, we can kind of work backwards again and see how much, this is the initial kinetic energy, the final kinetic energy. So, okay, this is the change in K, which is equal to K final minus K initial. So K initial, K final is going to be 0. So K, the total K is equal to negative because there's a minus sign here. 1/2. Now there's a new mass, 120 kg times this 4.083 meters per second, and this whole thing has to be squared. Okay, let's calculate that. 0.5 times 120 kilograms times 4.083 times 4.083. 1,000 exactly. And I'm gonna just round it. 1,000, and this is gonna be kilograms meters squared seconds squared, and this is gonna equal to the change in delta U. It's basically like we got a new velocity. Now we're gonna do this same method over here where we found the velocity, but backwards to find the angle. Does that help us? So U final minus U initial is going to be, I'm going to do a big M because it's now we're always working with their combined mass. mg L, and then again, should I do final? But it's a little different, so yeah, the minus sign comes in and flips things, so we're just going to get this equation. 1 minus cosine of theta. Now we solve for theta. Oh my god. Sorry guys if this is a crazy thing. Like I said, I didn't want to do it with so much detail, but there's, I guess, no other way to solve the problem. So 1,000 divided by 120 kilograms, which is the combined weight, divided by 9.81. So the weight cancels the kilograms. The 9.81 cancels one of the meters and both of the seconds, and we're left with meters. And then we divide by 5 meters. That cancels the meters. We get 0.16989. So 0.16989. This is equal to 1 minus cosine theta. So cosine theta is equal to, if we move cosine theta to the other side, we get 1 minus 0.16989, which is equal to 0.83011. And now we have to do a cosine inverse. So how do we do inverse cosine of 0.83011? And we get theta is equal to 33.89 degrees. Oh boy. Okay, well, it's definitely less than 60. Half, he picks up a girl that's almost his weight, so the angle drops almost to half. I don't know, but you know what? This is good enough. We don't got enough time to yap about it. So that leaves us with the Michael Jackson, the ball, and this bastard spring problem, bro. I don't like this one. Alright, let's take a look at this. How are we doing on time? 2 hours, 3 minutes. A cylinder of mass m, length L, radius r rolls without slipping on a flat surface. VCM 5. Friction between this. Man, I'm almost losing energy here. And then reaches a rough inclined surface. Alright guys, you know what? I'm gonna stop here because I feel like I'm just gonna think for the next hour, and this video is actually gonna be 3 hours long. And I don't know very clearly how to solve this number 11 with the spring. Okay, maybe I have some ideas, but they all seem to be wrong. I don't know what to do with this one. Maybe I can slam it a few more times. And I'm not too sure what to do with this Michael Jackson. And I also don't know the solutions to any of this. So after this video, I'm going to plug in this PDF into like some AI, see what the answers are. And maybe I'll put that right here. But I don't know, if you guys see the answers or if you guys compare your answers with mine, let me know if you see any discrepancies. Let me know if you have any ideas for the Michael Jackson problem. The point of this video was to just show you guys how I think about problems like, I don't know, it kind of maybe felt a little stupid now that I did it. my point was to very quickly go through the whole exam, which is kind of what I did, but I ended up going like each individual multiple choice question one at a time, which I don't know. It depends on the vibe, you know. Sometimes I very quickly, since I'm speaking in this video, like I wanted to read out every problem, and then when I read it, I was like, you know what, fuck it, let's just solve it. But in the exam, since I don't have to read out to anybody and I can just read faster by scanning the text, I will read it, and in my mind, I'm going to be like, do I understand what to do for this problem? If I do, I'm going to very quickly write something so I don't forget what my initial train of thought was. Like maybe I'll have a hunch or an idea of how to solve the problem. But I'm going to keep going through and just read everything so I have a vantage point of the exam. So for the first 10-15 minutes, I'm going to very quickly scan every problem so I can see all of them. Then I'm going to go through multiple choice first, do the multiple choice, leave the long answer. I don't know how you guys do exams, like you can do it your own way. Maybe you could do the long answer first, but then you kind of screw yourself because the multiple choice are a little hard as well. Then I do the long ones, I do the easy ones. If I ever get stuck, if I get stuck for like 1 minute or anything like that, I move to the next thing because you don't want to get stuck and just think. Right now I'm stuck and I'm thinking, but at least I solved almost everything. I have 3 questions left. So if everything else is right, then I don't know, I get around 70. I think, I'm just guessing. I always underestimate this shit, so I feel a little better. But anywho, try this out on the test. Like I said, use whatever you can. If you ever get lost, just isolate all the things that you have. If you get completely lost, isolate the things that you have. Put any equation that you think has anything to do with the problem. Torque, angular momentum, energy conservation shit. Like you guys saw a bunch of stuff that I use in this problem. You still could see a bunch of other stuff like with this Bob and Alice thing. I thought it was torque. I don't know. It looks like this is an equilibrium problem. And in equilibrium problems, you have torque conservation, which in this problem doesn't make sense because they don't give you a length for Bob, unless I'm just completely missing it, but I don't see a length for Bob. And you have sum of Newton's laws, which kind of makes sense here. Yo, hold up. We can do sum of Newton's laws. So over here, Bob is being pulled down, and he wants to slide this way, but friction is pulling him this way. So on the free body diagram, we have Bob is being pulled this way, friction is pulling him this way, and this thing is pulling him this way. So this has to exactly equal this for conservation to occur. And he also feels a normal force up here. So okay, this has to exactly equal this. What is the tension in the rope? It's exactly equal to, oh my god, we just did it, guys. Okay. So just using Newton's second laws, there's a force going this way and there's a friction force going this way, right? Because he wants to slide this way, but friction is keeping him this way. So there's a friction force here, there's a tension force here. And those are the only forces acting in the x direction. So tension has to exactly equal to the friction force. And the friction force is equal to mu times the normal force. And the normal force equals mg. So we have this is equal to this. I think that makes sense. Let me just write that down real quick. So tension is equal to 0.5 times Bob is 50 kg. But they say Bob is a uniform straight rod. And when I think about rod, like we haven't used a rod here, like any kind of a rod model. So that spooks me a little bit, but I don't know. We're going to put this. And then mg 9.8 meters per second squared. And this gives us kilogram meters per second squared. I think this is mass times acceleration. This gives us newtons. So yeah, that looks good. What is the minimum angle theta for which Bob does not slip? So think about this. As the theta decreases, how is theta going to be used here? I'm not sure, but anyway, like I said, I don't want to think about this too much anymore. I hope this video was helpful to you guys. I'm going to plug this into Gemini or ChatGPT or something, put what they give me here, see if I got anything right. And like I said, good luck. Try this out on the exam. I know that I probably have a lot more experience than you guys since I've done the class several times. I've read the shit. I'm trying to tutor it to you guys, but you guys can do this. And don't leave anything blank. Like here, if I'm at this stage and I have no idea what to do, For this one, I'm just gonna circle something. Like I don't know which one I'm gonna circle. I'm gonna try to pick the best one, and then for this one I think I can just finesse something. Like I can write a bunch of shit and overwhelm the grader, and then get some good grades out of it. All the other stuff, I think I feel pretty good about the solutions, and then the only thing that's left. So we did that. We did this. The only thing that's left is the Bob thing, right? Yeah, the only thing that's left is the Bob thing, and then we have this thing right here. So we're left with a few little things here, but thank you for watching this immensely long video. Thank you for staying with me this entire semester and helping me out. I hope you guys learned something interesting. I'm here at always. Anything you want questions about. It doesn't even have to be physics related. You can ask me anything in the comments. I will respond and try to help you guys out. And good luck on the exam, guys. Like always, please stay hydrated. Eat an orange, eat a banana, go say hi to your family. Look outside at the birds flying in the sky. Enjoy the weather and be happy and get that like weight off your chest. Stress is not good, so just try to relax, try to have a good time, and I'll see you guys next time. Thank you for watching. Peace. What's up, guys? It's the next day. I just finished editing this whole video right here, and I did make some mistakes. So let me pull up. This is me putting this into Gemini. I'm gonna go through it very quick. Multiple choice. Both objects, ball and bullet, fall at the same time. I think that was good. Projectile velocity, we got 111 meters. I think that was good. Maximum speed on a hill, we got 10 meters. That was good as well. Inelastic collision, 50%. We got that. That's awesome. Airbags, this was answer B, and I think I put answer B first, but then I was flipping around and I put answer C. So read answer B, try to convince yourself this makes sense so that on the exam you know what the answer is for airbag problems. Conservation of angular momentum, B. When a bird lands, the thing decreases, the angular speed decreases. I think I said that because I was imagining spinning around and someone giving you a big weight and you slow down. Rolling versus sliding, this one I think I got wrong. For the box, the potential energy becomes translational. For the rolling ball, the potential energy is split between translational and rotational. So split, when I thought about a ball rolling, translational and rotational kinetic energy, I thought more kinetic energy means faster, but it turns out that that's not the case. You actually split the energy, which makes the ball, the center of mass velocity of the ball, slower. So this is the one I got wrong. So I think 2 multiple choice wrong so far. Center of mass, both systems have the same initial linear momentum because the bullets come to rest. Okay, so this is the one where you shoot that block of wood. Check out the Veritasium video. Just search up Veritasium. Bullet shot in block rotational versus translational momentum or something like this. You should see the video, but this one I think we got right. Angular speed of connected magnets, omega over 8, we got that right. Simple harmonic motion, negative 6 pi meters per second, we got this right as well. Speed of applied force, this was question 11, I did not get this right, but it turns out you have work kinetic energy conservation theorem and you use px. So the work provided by this applied force and the work done by the spring. This question is confusing to me, but I did not get it right, but it turns out this is the answer. Also, don't trust AI. There's a little error I saw a little bit later in this AI thing. AI is trained on the entire internet, I think, so it's trained on correct things and incorrect things, so I could give you something incorrect. This is me just very quickly looking at some rough answers because I don't have the solutions at hand. But it looks like if we get the same answer as the AI here, either we're both right or we're both wrong. I think there's a higher likelihood that we're both right, but this one we did not know how to do. So I think that's 3 multiple choice incorrect. Linear acceleration on a disk. This one I also got wrong. So there's a tangential acceleration and there's a radial acceleration. All I found was the tangential acceleration, but acceleration is a vector. If there's multiple accelerations, you have to add them up, in this case using Pythagorean's theorem. So I got this wrong. I only got one of them. I think I got the answer as 16. You have to use this radial acceleration, which uses that number that we didn't use that I thought was put in there to trick you. And then you use both of these like legs of the acceleration vector or triangle, and then you combine it to get this. So I think this is 4 multiple choice wrong. Oof. Kinetic energy comparison. This one I also got wrong. Super silly. I just very quickly went through it and I chose Ka equals 4 Kb, which should have been Kb equals 4 Ka. I think my logic for this problem was right. I just very quickly went through it and I didn't see that the masses were different or whatever. So check out this problem, see if it makes sense. So I think that's 5 incorrect. Bird and insect, 6.8 meters. I think we got this correct. And then 39, we got this correct. So 5 out of 5 incorrect out of 15, 10 out of 15. So 10 times 2, this is 20 marks on the multiple choice out of a total of 30. Not bad, I don't think. I don't know, we could have done better. Let's check long answer. So free body diagram, that's okay. And then mu s here, they factor out g, and the g's get canceled, but I think this is the answer that I had, so I think this is good, and I think free body diagram is good as well. So that's correct. That's a whole 10 marks right there. So that brings us up to 30 out of 100, I believe, if I'm not mistaken. 30 out of 90 maybe, because the long answer is 10 each, and there's 6, so 60. And then the multiple choice is 30, so 90. I'm not sure, it doesn't really matter. Rolling cylinder, this one I don't think I got it at all. So yeah, there's some work, kinetic energy conservation thing, and then they get 2.05 meters as the thing. It looks like they found the kinetic energy at the beginning, and then they used this work, so mu k times, so the force of friction times the distance. That was the important thing, where you can pull the distance out of it. So this is a strange problem because there's forces, there's work, there's kinetic energy, there's force of friction, so a bunch of interesting things. Take a look at this problem again, try to do it. I'm talking to me personally. If you guys did this problem, no stress, but that's one completely wrong, so that sucks. Tarzan, 33.9, we got this right. This was an absolutely beautiful problem. I love this one. Conservation of energy, gravitational potential energy with kinetic, and then conservation of angular momentum, and then some trigonometry. Beautiful problem. We got this completely right, gang. Angular speed after impact, 44.55 radians. I think we got this, except I didn't put radians at the top. I just put 1 over seconds, but I think this is good, so this is another 10. So far we got 30 points out of the long answer. That's pimp. Anti-gravity lean. This one was a bit weird, and check this out. This is what I mean by AI makes mistakes. They use L in their problem when L was not given to you, and then they say part A requires a specific angle theta, which is not clearly visible in the prompt, but I don't think it was given the theta. So this idea, the way Gemini is solving this problem, is incorrect. Non-slip conditions, I don't know. This Michael Jackson problem is strange, but we got it completely wrong. We didn't do it. Spring on an incline, I think this one I got wrong as well, or Gemini's giving me a different answer. I got 19.6 centimeters. I think I got 9 centimeters. And then here, 6.04, I think I got 0.5 meters per second. So this one is wrong as well. So I think 30 marks from the long answer, 20 marks. I got 50 out of 90. That's rough, bro. That's like barely passing. Anyway, hopefully this video was cool for you guys. Good luck on the exam, guys. Let me know, as always, if you have any questions. I know the exam is tomorrow, so grind and then focus on your other exams and enjoy the summertime. Thank you for the help in this course. I'll see you guys later. Peace.